Okay, I hope that everybody can see my my slides. So I change my title to some topic in spectrograph theory. So the goal of this course is that in my first lecture I will talk about the basic spectrograph theory, and I will prove the Perron-Frobenius theorem, for example. In the second lecture, I will look at interlacing and equatorial partitions and give some applications of all those things. And in the third and the fourth lecture, I will talk about distance regular graphs. So I will start with basic definitions. So I will start with definitions. I will try to do part 1 today. So maybe it's possible, maybe not. We will see how far I come today. So definitions. Okay, so for me, a graph is a finite, simple, undirected graph. So there are no loops or multiple edges, and everything is undirected. We need things for connectedness. We need the distance between x and y, that is the length of the shortest path connecting them, and the diameter is the maximum distance occurring in the graph among if you look over all the vertices. We call an induced subgraph if it's a subset of the vertex set and all the edges that have both endpoints in U. So that is induced. For us, induced subgraphs are very important. And a maximal connected induced subgraph of a graph is called a connected component of the graph. And for us, if you have a graph whose graph C, whose connected components are H1, H2 up to HT, then we take the adjacent matrix as a diagonal matrix, block matrix with blocks H1 up to HT. And the spectrum of this graph C certified that it's a union of the spectra, where I mean by the union if say one is also an eigenvalue with multiplicity say 30 of H, so H2, then one has 30 multiplicity 10 plus 20 or 30 plus. Yes, we add all the multiplicity together. And we will look at, so we look at Z-axis, the neighbors of a vertex X, that are the Y, that XY is an X. And Kx, which is the valency, is the number of neighbors of X. So we call that the valency. I don't like to call it the degree, because degree has so many meanings in mathematics. You have the degree of polynomial, the degree of the angle. So I prefer to talk about valencies instead of degrees. And an important subgraph is a subgraph induced on the neighbors of X, and we call that the local graph at X, and usually denoted by delta X. I will need this in the third, in the distance regular graph part. Okay, I should have first introduced it. Adjacency matrix. Okay. So adjacency matrix is a symmetric matrix A indexed by the vertex set such that AX y is 1, the xy entry is 1 if x is associated to y and 0 otherwise. And we say the eigenvalues of A are called the eigenvalues of G. Yeah, then you say, yeah, but you may have many different A's because you can commute the vertices, but they are all similar to each other, those association matrices, so the eigenvalues don't change. So it is a proper definition. And note that the eigenvalues of G are totally real algebraic integers. They are real because symmetric, and they are algebraic integers because the leading term of the characteristic polynomial is 1. So that's an algebraic integer such that a total real algebraic integer is algebraic integer that all its minimal polynomial has only real roots. So an example is square root of 2, but if you take the third root of 2, then you get also complex roots. So that is not a total real algebraic integer. And if they are algebraic conjugates, that means that they are in the same, they are roots of the same minimal polynomial, then their multiplicity must be the same. This is easy to see. We say that the graph is k-regular if the valency of every vertex is a non-negative integer k. Usually k is 0. We try to, yeah, we don't really like it, but that's all. And you can easily see that that eigenvalue k, that eigenvalue k as a. If I look at the association matrix and I multiply by the O1 factor, then I can get k times the O1 factor. That is. So in spectrograph theory, we don't to find eigenvalues, we don't use the characteristic polynomial of the association matrix. So we usually try to guess the eigenvalues and then prove that they are really eigenvalues. And you will see how you can do this later. So now I want to talk about what kind of graph properties can you see from the association matrix. So I look at AT and then XY and 3. I take the association matrix and I A times A times A and then T times, and then I take the Y entry of that matrix. That is the number of walks of X to Y of length T. That means you go from X to X1, X1 to X2, X2 to X3, and so on to XT, and that is Y. And that number of walks. And this you can easily prove by induction on T. It is, for T is 1 is trivial, and then you do an easy induction. It's not difficult to prove this. And what you learned, there's a mistake here. The trace of AT, the XY should not be there. I'm sorry, I forgot to remove it. You're right. Okay. So what you can see easily that the trace of AT is the sum of the eigenvalues of the association matrix, that is theta I to the power T. So I assume that A has eigenvalues theta 1 to theta n. And another thing you can easily see is that the trace of A must be 0 because X can never be associated to X. And then you can see that by using the number 2, you see that the trace of A squared is 2 times the number of edges, because that's the sum of the degrees of vertices, yes. And that's 2 times the number of edges. Every edge has 2 endpoints. Yes. And similar way, you can see that the trace of a to the power 3 is 6 times the number of triangles in T. So you can see the number of edges, the number of triangles. What about the number of quadrangles? Can you see that as well? So here is 2 graphs. This is the smallest pair of 2 graphs which are not they have the same spectrum but are not isomorphic. So they look very different, the 2 graphs, T1 and T2. They are very different graphs. Yes, one is a quadrangle with an isolated vertex, and the other one is the K14. Yes, 4 claw. Yes, and here under you see the adjacency matrices. And it's not so difficult to prove that they have really spectrum 2, 0 to the power 3 minus 2. But I'm not going to do that today. It would be a nice homework for you to do this yourself. It is not difficult to prove this. And I will give many ways to prove it later, so don't worry. So what this says is you cannot see the number of induced quadrangles. You cannot see whether the graph is connected or not, because one was connected, the other one is not connected. And you can also not see the degree of the sequence of valencies, because one has 1, 1, 1, 1, 4, the other one has 2, 2, 2, 0. Yes, as the valencies or the degree of the sequence of valencies. So now I will talk about the spectral radius of a graph. So we call the last eigenvalue of T the spectral radius of T, and we denote it usually by a rho. We will see the reason why this eigenvalue is called the spectral later as we discuss the Perron-Frobenius theorem. We will prove the unsymmetric virtue of the Perron-Frobenius theorem because that is a much easier proof than if you want to prove the Perron-Frobenius theorem in all generality. You have to use continuity and a lot of the different parts of. You have to use some analysis. You have to look at limits and so on. So, but if you look at the symmetric version, everything becomes much easier. So now we look at the connected graph, and so I want to look at the following results on the spectral radius of a graph. So let's see the connected graph of order n and size m. That means the number of edges. So it has m edges and n vertices. Let rho be the spectral radius of T, and delta, capital delta, be the maximum valency of T. Then rho is between 2m over n and capital delta. And equality holds in one of them if and only if it holds in both of them, if and only if the graph is the capital delta regular. Another result you can prove is that it at most is square root of 2m times m minus 1 over n. And you have equality if and only if it's complete. So let's prove this lemma. It's not difficult. So the first result says that you can, if you have connected graph, you can see whether it's regular or not for the spectrum. So what do we want to prove? So we assume that we have an eigenvector for the spectral radius, and let x in be a vertex of T such that the phi of x is greater or equal to phi of y. And of course, it is greater than 0 because I say without loss of generality, but you have it without loss of generality. You can always see it. We have Vx bigger than 0. So now we find the following equation. Rho times V of x is AV of x, and that is V, the sum over y, which are changed to x, Vy, and that is a most delta x, yes, because you have a most delta of delta neighbors of x, yes. So we get this is and Vy is the most Vx, so we get easily this. And equality holds if Vy is Vx for all y are changed to x. As the graph is connected, we see that the graph is delta regular. That's all. Now we will look for the second inequality. So this is a Rayleigh inequality. So if I look at the all1 factor A or 1 factor over the all1 factor in product itself, that's exactly 2 times the number of exactly number of ones in A, which is 2 times the number of edges. And the second one is clearly n, so that is 2m over n. And because this is always true, because you have always that the last eigenvalue is always greater or equal to any factor v transpose A, v transpose times v for any non-zero factor. So, and what happens if if and only if O1 factor is an eigenvector of A, and this means that the graph is K regular, or you can say 2m over n regular if you like that better. This shows the first item. So this is not a difficult proof. Don't worry, the proof gets much more difficult later. So now we are going to prove the second item. So what do we have? We have some of the eigenvalues is 0, that is the trace of A, and the sum of the squares of the eigenvalues is 2m, that is trace of A squared, yes? So that means that if I put the row on the other side of the equation, we get this, we have these two equations. Then we use the Cauchy-Schwarz inequality, and we see that we get this, yes? Or maybe I should have said minus rho over n minus 1 instead of rho over n minus 1, but that is a small difference because the minus 1 disappears if I do square, so it is exactly the same. And what happens? Equality happens even only if theta I is rho over n minus 1, and it's not difficult to see that a graph with two distinct eigenvalues must be complete. And this equality is equivalent with rho is at most the square root of 2m times n minus 1 over m. That's not difficult to see. It is a little bit, you calculate, and then you see it easily that it is true. And if equality holds, then you have only most two distinct eigenvalues. Then everybody should rho theta 2 up to theta n should be all minus rho over n minus 1. Okay, now I will discuss bipartite graphs. So a graph is bipartite if there exists a partition into two parts, say the red and the blue vertices, such that each edge has one red vertex and one blue vertex. And if you have a graph without any edges, also bipartite, but it is very so that is if the graph is in collection of isolated vertices, is also bipartite, but that's not so interesting graph. But so you cannot say that it is always too colorable. I will discuss this later, too colorable later, but for now, let's not worry about too much. How can I recognize a bipartite graph? That was shown by Orr. Graph is bipartite if and only if there's no close walks of odd length in T. And the proof is very easy. The one direction is by definition. And then we take a vertex X, and then we define the red vertices as the one that has distance an even integer 2x, and the blue vertices are with an odd distance 2x. So as there are no closed walks of odd length in G, the sets R and B are independent. That is, there are no edges inside them. This implies that G is bipartite. Can we recognize bipartiteness from the spectrum? That's the next question, yes. Yeah, I will show you can. The graph is bipartite if and only if the trace of a to the power 2t plus 1 is 0. If all the odd powers of a have trace 0. And the trace of a, as I already know, is the sum of the diagonal entries. So now we give a spectral characterization of bipartiteness. A graph G is bipartite if and only if for each eigenvalue theta of T with multiplicity m, the number minus theta is also an eigenvalue of T with the same multiplicity. So it is symmetric around the 0. That's what the spectrum is, symmetric around 0. And how do you prove this? So let's see be bipartite with respect to the red and the blue vertices. Assume AV is theta V. Then you define a new vector with x entry is the x entry of V if x is in the red vertices, or minus V of x if x is a blue vertex. And then you can easily calculate that the V1 must be prime must be an eigenvector of A for eigenvalue minus theta. And so now you assume that you have a V1 to Vm linear independent eigenvectors for theta, and assume that alpha V prime 1 plus alpha m P prime m is 0, then you get these two equations. It depends whether x is red or blue, but essentially it's the same, yes. So then this means that it is 0, all the alpha i's are 0, which means that the multiplicity of theta must be equal to. This shows that multiplicity of theta is at least, or at most, the multiplicity of minus theta. But then you interchange the whole of minus theta with theta, and then you see that you have the older inequality as well. Now you assume for all eigenvalues theta of the multiplicity theta is equal to the multiplicity of minus theta. Now we need to show this bipartite. Yes? So then you calculate the trace of a to the power 2t plus 1. That is the sum over theta, the multiplicity of t, but the multiplicity of theta times theta to the 2t plus 1, yes, that is exactly the trace of that number. So now you put, because you know that theta minus theta has the same multiplicity, so you see that this is the sum where theta is bigger than 0 over multiplicity of theta times theta to the power 2t plus 1 plus minus theta to the power 2t plus 1, and that's equal to 0. And therefore, by the theorem of Ohr, the graph must be bipartite. So I missed this section in my other talk, so somehow the processing was not done well. I'm sorry. So now we will do this this section. Sorry for the interruption. So we have seen that in connected graph C is K regular if and only if K is 2m over n. Is the last eigenvalue of C, where n is the order of C and m is the number of edges of C, or the size of C. Now we give some properties of K regular graph. So let C be K regular graph, then the following holds. K is an eigenvalue of C. The multiplicity of K is the number of connected components of C. For all eigenvalues delta, we have G is we have that all the eigenvalues are in absolute value and most K. We have that multiplicity K is always at least a multiplicity minus K. Is bipartite even only if the multiplicity. So you can see quite a bit of already before. What was the first item? Yes, that K is an eigenvalue of T, that because of all one factor is an eigenvector. Now we assume that C is connected. We will show that the multiplicity of K must be equal to 1. So let A is K times X. AX is K times X. And assume that Xi is the lastest of all the Xj's. Then you can see that you have this equality. Yes, we already have seen this before, this kind of equation. And hence Xj is Xi for J is J to I. So as the graph is connected, we obtain that Xj must be Xi for all J and I. Yes, for all J. So now we show that all the eigenvalues are most K. So now we assume that AV is theta phi times, yes. Let I be the maximum, that phi I in absolute value is the maximum of phi J's. And we may assume with our lossless reality, we have phi I bigger than 0, because if it was negative, we can always multiply the eigenvector with -1. And then we get, that's still an eigenvector. And then we have these equations, yes. So theta in absolute value times Vi is AV, absolute value of AV in position I. And that is the absolute value of the sum of Vi J's. And then you can put the absolute value inside, and that's always smaller, equal to the where you put the sum of the absolute values together. And that is a most K times Vi, yes, by definition. This shows that the theta in absolute value is the most K. Now we will show the last two items of the properties together. So without locality, we may assume that T is connected. So we have okay. So we have shown that multiplicity of K is 1 if it's connected, and therefore the multiplicity of K is normal connect components. So now we want to show them for bipartite that the smallest eigenvalue, the minus K, has multiplicity at most the multiplicity of K. And we first do it for when T is connected. Then we have to show that the multiplicity of minus K is at most 1. Yes. And if it's 1, then it is bipartite. So now we should assume that A times U is minus K times U, with U is not 0. And I assume that Ui is greater or equal to Uj for all K which are not equal to I. That Ui in absolute value is the largest of everything. Then it's also difficult to see the following equations. Yes. So this is as easy as we had before. And as T is connected, we find that Uj is Ui, and that shows that the multiplicity is of minus K is 1. And we can define these two sets, the red vertices and the blue vertices, where the red has all the positive entries and the blue vertices all the negative entries. Yes. So it's clear that R and B are both independent sets. Hence, T must be bipartite with respect to the partition R and B. This finishes the proof because if it's not bipartite, then we get the multiplicity of minus K is 0. And if the multiplicity of minus K is 1, then it's bipartite. That we have shown. So we have shown the proposition. So now I will discuss the Hoffman polynomial. And this is the following result of Alan Hoffman of 1963. I think when almost all of you were not even born. Okay, so what did he prove in 1963? So you take G to be a graph, then the all-one matrix K is in the Artesian algebra A. That means the algebra that consists of the polynomials in A with integer coefficients. That's the Artesian algebra. I'm sorry, I did not define it. If and only if, so what we want to say is K is a polynomial A if and only if T is connected and K regular for some K. So we prove first the second part implies the first part. So we assume that T is connected and K regular. Let K is theta 0 greater than theta 1 greater than theta D be the distinct eigenvalues of T and for some integer D. Then we can look at the sum of eigenvalues I is 1 to D over the product from 1 to D of A minus theta I. Yes, this I claim is a constant times the O1 factor or O1 matrix. Why is this true? Because the O1 factor, if I multiply the O1 factor but with this matrix, that I get a constant times the O1 vector. Yes. So, and the other eigenvectors disappear. So it must be constant times the O1 matrix to be all. It should be in the eigenspace of this matrix. So therefore, you get a constant by the O1 vector or O1 matrix. That means that J is a polynomial A, and therefore this is Artesian algebra. Now let's say to be in the Artesian algebra, that means that J O1 matrix is a polynomial A for some polynomial P. Let PA be alpha 0 times I times plus alpha 1 times A plus AT alpha T times A to the power T for some alphas. Yes, so we have the O1 vector, and then we can write it as a sum of powers in A. Then PA, if I look at the XY entry, is 1, yes, because that is by definition. That means there exists an R such that x to the R, xy is not 0. This implies that x and y are connected by some part of length R or walk of length R, yes? And hence the whole graph must be connected. Another observation is that if I multiply A, K on the left hand side or the right hand side, that doesn't make a difference because K is a polynomial A, yes? It makes no difference whether I write it in the left or the right. The same, you get the same polynomial in the end, yes? So then that means that Kx, that is Aj in the entry X is Kx, that is Ajxy, yes? But that is also JAXY, and that's KY, so KX must be KY. And this shows that X and Y, that T is regular, K regular, because T is also connected. We already have shown that T is already connected. So now we can define the Hoffman polynomial. So we have a K-regular graph of order n, say, with distinct eigenvalues K, θ1 up to θd, T. Then we can define this will be in D, not the D, I'm sorry. So this will be K, θ1 up to θd. Then if I look at this product, I see that that must be equal. If I look at the product I to D of A minus theta I, then that is K minus theta I, that product over N. Okay, so that is. So I will not prove today the Perron-Frobenius. I will start that with tomorrow, but I will discuss the Perron-Frobenius today. But I will not prove it today. I think it's better because that will take about half an hour, and I really go much over time if I do that. So we now present a symmetric version of the Perron-Frobenius theorem. And we only treat the symmetric version as we only consider symmetric matrices in this course. We don't care about non-symmetric matrices. The proof in this case is much easier than if we allow asymmetric matrices. So the proof is all about 30 minutes, I think. So what do we need as our input? We have a symmetric matrix that has all non-negative entries, and is irreducible, that means there is a power m so that C plus I, the identity matrix, to the power m is greater than 0. And we look at the theta 0 as the largest eigenvalue and theta min as smallest eigenvalue. And let's see the graph with respect to C, so that AGIJ is 1 if and only if CIJ is greater than 0. We allow the case EHJ in this theorem if so may have contained loops, but it's in the only graph in this whole course that may have loops. So only in this theorem I allow loops. Yes, so then the graph C is connected as C is irreducible. Then we have the following 6 statements. I will not look at all of them now, but maybe I can prove the first 2 today and then I will prove the rest tomorrow. That's maybe a good way to compromise. So the first 2 is there exists a positive eigenvector for the eigenvalue theta 0. And the multiplicity of theta 0 is exactly 1. That is what I will prove today. And then tomorrow I will prove the rest of the theorem. That probably takes about 10-15 minutes. So we look at the matrix D, which is theta 0 minus C, is positive 7 definite. That means that D is n transpose times n for some matrix n, with columns V1 to Vn. So hence the D is the gram matrix. That means that the DIY entry is the inner product of Vi and Vj. That's the same thing, just difficult words. First, we show that if I look at the sum of I is 1 to n, alpha I times Pi, that is equal to the 0 factor. So how do you prove this? So you look at phi transpose n phi transpose, yes? That is phi transpose times d times phi. That we can write now what is d, then is theta 0 times identity minus c. That's this. Because c phi is theta phi, so we get that this is 0. Yes? So that means that NV is 0. Yes? This means NV times NV, the inner product is 0, and hence NV is 0. This shows that the sum I is 1 to n alpha I Vi is 0. And I assume that alpha 1 is greater than 0 without loss of identity. There exists an integer s that alpha I is greater than 0 for I is smaller or equal to Sn. Alpha I is smaller or equal to 0 if I bigger than that. And we want to prove that this S does not exist, or yeah, that we want to show that S is equal to n, yes, to the order of the matrix. So let P is alpha 1 plus V1 plus alpha 2 times V2 plus alpha 3 times V3 up to alpha SVS, yes, and that's to be equal. And that is equal to the minus sum of the other ones, yes? The sum. So then we can try to calculate this, yes? So we see that that is minus the sum over S plus 1 to n alpha j times dij. And that is, so we first assume I is a most But then we calculate this, we can write the definition, but because I is not equal to j, we see that the theta I part disappears, and then the two minuses disappear with each other. So that is sum over s plus 1 over n times alpha j times Cij. And alphas are all negative and theCij's are all non-negative, so these are most zero. So that we see that this inner product is a most zero. Yes. So why do we now get that P is equal to 0, that P is the zero factor? Because if I look at P times with the inner product with P, that is same as looking at P with the sum from I is 1 to S alpha Vi. Yes. We had this Vi times Pi is more to 0. So this all the alpha i's are all positive, and the Vi's P is negative, so this is negative. So we get this equation. Yes, like before, we get this equation, and then we see that something should be smaller to 0. But the main point is that now we get that sum I is 1 to S alpha I d ij, or what I should say that the sum I is 1 to S alpha I Cij is 0. So that means that, what is this for strange thing? So we take K is in S plus 1 up to N. Then we see that the Cij must be smaller to 0. But alpha i's are positive. So that means that the Cij must be 0. So there are no edges between the set 1 to S and the set S plus 1 to N. So that means that the matrix is irreducible. And this is a contradiction with our assumptions. So this means that all the entries are positive. And this shows 1. And also 2, the multiplicity of this eigenvector is clearly 1, because that's only one eigenvector, and that's positive. If there are 2 eigenvectors, then one of the 2 eigenvectors has to have at least an entry 0. Yes. So I will stop here for today, and I will go further tomorrow with this proof, and then I will start to look at interlacing and other things. Okay, thank you for your attention.